This is the EDX engineering simulation course, and the main focus here is to move from pushing a button to thinking like an expert. This is hands-on, however, as I'm on a tablet, Ansys wouldn't work here, but might as well learn about it. So starting with the interview with the Ansys founder, these are my notes on it. Okay, so in simple terms, Ansys started because there was a problem, an engineering problem, and he needed to find a tool to solve that problem, and he couldn't. So therefore, he made it himself. Ansys has all the requirements and features that an engineer needs to design or make maybe a test for whatever product they want to create. This includes whatever material you're using, working with, whatever maybe shape you're working with, cylinder, or whatever it may be, it's applicable here, and whatever mathematical model, which would be heard later on, will be used as well. So that's what it means by a software package applicable for all designs, basically. So yeah. So I decided to take a step further and search what is Ansys anyway. And here are some results saying it's an analyzing software that provides the user with understanding of whether their product will work or not. And this is used a lot when, rather than doing an experimental physical experiment, which is quite expensive to test whether the material you're using is applicable, you can just test it on the software and it would work. And it uses both physical properties from physics and also working out from maths to solve this quote-unquote mathematical problem. And these are some examples of what it can be tested for, such as the strength, elasticity, toughness, and these are principles in physics as well which are used. And yeah, this is what Ansys does. And in this course, the speaker mentions a lot about the black box, and that's basically the application of Ansys. Ansys is the black box, which would, you could say, work out what you want it to work out. So that's how it's basically related to. But in this course, it's also about understanding how Ansys works and how to use it. So this is just an overview of what Ansys is and basically linked to the interview. And yeah, here it mentions where more stress, so if you have a certain material, if it's thinner, then that means it could take less force and the stress needs to be less. But if it's maybe thicker or it's a wider area, then it's more usable. And linked to the reliability and modeling, so rather than doing it in real life, you could just do it in the software, and the software will give you the accurate results, and it'll be faster too. So I wrote product over here, but this could also be exchanged for material. So if you want to test the material out before you use it, so it's not just the product. So just credit to this website and the writer, because this is where I got information, extra information of what is ANSYS and more information about that. So moving on to the black box, which I mentioned earlier, and these are my notes on it. So what is the black box? Particularly as I have finished a percentage also of this course beforehand around last year, I'm going to be using my prior notes also, as well as reminding myself of the videos by rewatching them and making basically a presentation on it. So I've started over here with the input in this box in the middle, supposed to be the out and black box, and then the output. So the input of the black box is any information that is needed for your mathematical model to work. So here in yellow it says material properties, so whatever is suitable for your products, and as mentioned before, it's maybe the stress or strain it could take, any information concerning that. Then you have boundary conditions, so if it's a 3D shape or something, and it has to meet a certain criteria. What is that criteria? You need to make sure that all these informations are set into the input. Then the black box will sort it out, or as mentioned in the video, you will turn the crank of the black box, then you'll get an output. I see the black box very similar to a calculator. So basically you'll put in the input, then you'll get the output of the answer. Now the outputs, there's a range of outputs, but mainly what's mentioned is colored pictures. So basically the ones you'll normally see as engineered software designs or CAD designs, I suppose. I've got a few examples here. And yeah, this is basically the ANSYS or black box doing the work for you, and you've got your output, you've got the design, and the colors help you see maybe where more stress and strain is, I believe, but that wasn't really mentioned in this course. You also get other results, but that wasn't mentioned as much anyway. So the main objective of this course is to know what's happening under the black box, not just to use it as a calculator or just an easy way to get information. And therefore you also have to work with the mathematical problem as well. So that's what the next few videos or modules are going to be concerning, what's under the black box, and also using ANSYS to basically put yourself in the shoes of engineer and make your own mathematical problem, solve it, and then compare that result with the ANSYS software. So here I mentioned about the calculator and how I see ANSYS very similar to how a calculator works. If you know that the product of 9 times 9 is 81, then obviously you have an expectation of what the calculator is going to give you. But if you put, for example, a mistake in your input, you put 6 instead of 9, then you'll get a different answer. But if you don't look again to your input or do a pre-analysis, then you wouldn't be able to find where that mistake is. And if you don't do your own working out, you're going to be following that mistake, and it will cause problems with the design and whatever you're making, or whatever work is going, or whatever the input output is for the ANSYS model. Okay, so for the second session or so of the black box is how to know what is underneath the black box. So we know the framework of it, which is basically the framework of what ANSYS runs on. So now we need to know that, and up there is supposed to be a brain to know. So there's a few steps. One is to make a pre-analysis, as mentioned before. So making sure your input is right and everything. Next, then use the software output. Also, the pre-analysis helps you have an idea of what is expected since you know the right inputs being input. And then finally, you have the verification and validation, and that's when you do your own working out. Verification, you do your own working out, or you could do the experimental setup and make sure that the results are, that will be your, what's it called again? Reference results. So you'll use that as reference and see how close the output is to that. And the validation is making sure that the errors are not too much, or there's an acceptable amount of errors, you could say. Mention here, so going with an expectation, yep, so that's what you'll do. That's why you have a pre-analysis and basically following these steps to make sure you have an idea of what's happening. And yeah, normally considers mathematical reasoning. So I've drawn here the model that featured in the video. So you have the input and you have the mathematical model in purple, and that's what is being worked with. The software works with that and you work with that. So you have your physical problem, and two ways to work that out is you either do a calculation for it or you do the experimental method to find it. And then the mathematical problem in this box, which represents the black box, it will find a numerical solution, and then there'll be selected variables, and then it comes out with the output, which is your colored pictures. So that's basically the main framework or model of the black box here. So now the next section is the discussion and looking at what other students have mentioned. So here an undergraduate student asks how to develop mastery or skill in mathematical modeling, and I have the same question to that too. Here one person replied that mathematical methods for engineers, it's a free course given by MIT. And this final comment mentions that you don't need to have complicated equations to make sure that when you solve the mathematical problem, it's accurate. Rather, you could have, some people would use a few basic equations and get the answer, and you'll have better accuracy and it's more reliable than having a longer equation. So mathematical models doesn't always concern having complicated long equations, but rather you can just, when you can find an answer, and you can find a solution, and it's a simple and easy and perhaps also repeatable way to do that, then it's more useful.